Welcome to your journey toward achieving the CyberArk Defender certification. In this introductory module, we will establish the fundamental principles of privileged access management and outline the architectural framework we intend to master. This is an unofficial, independently produced course. It is not affiliated with, endorsed by, or connected to CyberArk in any way. All trademarks belong to their respective owners. If you are looking to validate your expertise in securing privileged accounts, you have landed in the right place. This course is specifically engineered to bridge the gap between theoretical identity, security, and the practical, hard-nosed requirements of the PAM-DEF exam. We will systematically deconstruct the CyberArk ecosystem, ensuring you understand not just how to click through the interface, but why the system behaves in specific, rigorous ways. Our focus remains on high-level architecture, efficient lifecycle management, and the tactical monitoring of privileged sessions. By the end of this curriculum, you will possess the requisite knowledge to excel in a professional technical role involving CyberArk deployments. Privileged access management is, at its core, a discipline of risk mitigation rather than mere password storage. We are dealing with identities that have the power to dismantle an entire infrastructure if compromised, which is why we must treat these accounts as the highest tier assets in the enterprise. The identity security landscape today is incredibly hostile, with automated threat vectors constantly scanning for hard-coded credentials, service account vulnerabilities, and latent administrative privileges. Our methodology involves adopting the CyberArk blueprint, an architectural roadmap that replaces implicit trust with explicit validation and isolated access. You will learn to view identity as the new perimeter where every session is accounted for and every credential is rotated according to strictly enforced policies. The CyberArk ecosystem relies on a modular architecture where each component serves a distinct, non-overlapping purpose to maintain a secure environment. The digital vault acts as the hardened heart of the system, storing both data and sensitive metadata in an encrypted, non-transparent format. Sitting atop this foundation is the Password Vault Web Access, which provides the user and administration interface while abstracting the complexity of the underlying storage. For automation and routine maintenance, the Central Policy Manager handles the heavy lifting of password rotation and verification against various target platforms. When a user needs to interact with the system, the Privileged Session Manager serves as an essential gatekeeper, providing session isolation and full audit trail recording. Finally, the Privileged Threat Analytics Engine monitors these activities to detect anomalous behavior, signaling a shift from reactive password management to proactive intelligent defense. We will move through these topics by defining logical workflows, starting from how we onboard accounts and ending with how we monitor active sessions. You should expect a deep technical dive that requires you to reconcile your current understanding of account lifecycle management with the strict compliance rules defined in the master policy. We are preparing for real-world scenarios where manual intervention is minimized and automated. Lifecycle management is prioritized through discovery and dependency mapping. This course is designed to equip you for professional-level tasks, including the deployment of security policies and the troubleshooting of connection components. Please keep in mind that our goal is total system stability and verifiable auditability across the entire credential lifecycle. I look forward to walking through these architectural details with you in the upcoming sessions. Welcome back. In this lecture, we will perform a deep dive into the CyberArk Privileged Access Security Architecture and examine how individual components interoperate to form a robust security ecosystem. At the heart of the CyberArk infrastructure lies the digital vault, which serves as the secure, hardened repository for all privileged credentials and configuration data. The vault is a proprietary server that utilizes a unique database and a hardened operating system to ensure that data remains inaccessible to unauthorized entities, even those with administrative rights on the underlying host. Communication between other components in the vault occurs primarily over the secure, proprietary CyberArk protocol using TCP port 1858. Understanding this architecture requires recognizing that no component communicates directly with the target system. Instead, they act as proxies or intermediaries that receive instructions from the vault and relay them as needed. This design ensures that the vault remains the single source of truth, effectively centralizing the security posture and auditing functions across the entire enterprise environment. The Privileged Vault Web Access, or PVWA, acts as the primary user interface for both administrators and end users who need to interact with the system. While it is often mistaken for a mere management dashboard, it is actually a web-based client that translates user requests into commands stored within the vault. The Central Policy Manager, or CPM, serves as the engine responsible for the automated management of credentials, such as rotating passwords or verifying that accounts meet organizational complexity requirements. By leveraging plugins, the CPM executes password changes on target systems based on the policies defined within the Vault settings. This automation is critical because it removes the manual toil of credential lifecycle management, thereby reducing the risk of human error or oversight during sensitive operations. Session management is handled by the Privileged Session Manager, or PSM, which provides a gateway for establishing isolated sessions to target systems. When a user requests access to a server, the PSM creates a hardened bridge, ensuring that the user never gains direct network visibility to the underlying target credentials. For Linux and Unix environments, the PSM for SSH offers granular command line control and session recording, enabling organizations to monitor and audit shell activity in real time. By sitting at the network perimeter of the target environment, the PSM facilitates isolation while logging every interaction, keystroke, and video frame for compliance and forensic analysis. This architectural choice effectively turns privileged access into a controlled, auditable transaction rather than a persistent network connection. Finally, we must integrate the Privileged Threat Analytics, or PTA, into our understanding of the architecture to complete the security picture. The PTA continuously monitors the activity logs generated by the Vault, CPM, and PSM, analyzing user behavior to detect anomalies that might indicate compromised credentials or malicious intent. By establishing a baseline of normal activity, it can trigger alerts or even initiate automated remediation workflows when it identifies deviating patterns. Integrating these components requires rigorous firewall management, as each service must be able to reach the vault on TCP 1858 while maintaining strict network separation via distinct hardening profiles. This interconnected system acts as a unified defensive layer, designed specifically to address the threat lifecycle from password discovery to session execution and threat detection. I will see you in the next lecture. Welcome back to our journey through the CyberArk Digital Vault architecture. In this lesson, we will focus on the fundamental concepts of safe design and the logical structures that keep your privileged credentials secure. To understand the digital vault, one must stop thinking of it as a traditional file system and start viewing it as a highly specialized, hardened, and encrypted database container. A safe is the primary logical boundary for storing privileged objects, functioning essentially as an access-controlled container that isolates credentials from other parts of the environment. When designing your vault structure, you are not merely organizing files, you are establishing the perimeter of your administrative control plane. Think of the safe as a unit of security policy, where every object inside inherits or shares common properties, such as retention periods or access lists. By grouping credentials logically, you minimize the blast radius of any potential misconfiguration. Proper architecture here prevents the common trap of creating a bloated, monolithic structure that becomes impossible to audit or manage as your enterprise footprint expands. If you ignore the necessity of a defined hierarchy, you will eventually find yourself fighting the system's inherent design rather than leveraging it. The naming convention you choose for your safes is one of the most critical decisions you will make for long-term scalability. A consistent, predictable nomenclature allows administrators to intuitively understand the contents and security requirements of a safe without needing to inspect its internal properties. For example, incorporating business units, environment types like production or development, and the classification of credentials, such as Windows, Linux, or database, can drastically reduce human error during onboarding. Without a standardized naming scheme, your vault environment will quickly entropy into an unmanageable state, making automation and lifecycle management significantly more difficult to implement. When you automate the onboarding of thousands of accounts, your scripts or API calls must rely on these predictable patterns to place objects in the correct containers. Aim for a structure that remains meaningful even when the person who originally designed it has moved on to other responsibilities. Safe properties like object history and retention periods serve as the guardrails for your compliance posture. The retention period dictates how long the vault retains the previous versions of an object, which is vital for forensic analysis and disaster recovery. When an account password is rotated, the CyberArk environment maintains old versions, allowing you to track changes and roll back if an unexpected application dependency breaks following a rotation. You must carefully balance these settings because overly aggressive retention will consume storage on the Vault server, while insufficient retention might leave your security team without the audit trail they require for incident response. Furthermore, enabling searchability for accounts within a safe allows delegated users to locate the credentials they require, provided they have the correct permissions. Balancing the security principle of least privilege with operational visibility is the cornerstone of a functional, high-performing safe design. Organizing accounts based on operational requirements and security boundaries is not a one-size-fits-all exercise. You should segment your safes based on the criticality of the hosted credentials and the specific administrative teams responsible for their management. For instance, putting high-security root credentials in the same safe as standard service accounts is generally considered a poor practice, as it complicates the management of access control lists. Each safe becomes an opportunity to apply a specific security policy that aligns with your organization's internal controls. By isolating accounts that share an operational lifecycle, you ensure that rotation policies, dual control workflows, and access permissions are applied precisely where needed. This granular approach is what separates a mature privileged access management implementation from a fragile, haphazard one. When you prioritize structural integrity now, you save yourself countless hours of troubleshooting and security auditing down the road. See you in the next lecture. Welcome back to our exploration of the CyberArk core architecture, where we will now focus on the granular control mechanisms governing safe access. This lecture addresses the architecture of safes and exactly how you should delegate permissions to maintain a strong security posture. In the CyberArk ecosystem, a safe acts as the fundamental logical container for storing privileged credentials, and managing who accesses these containers is the cornerstone of a functional PAM environment. When you grant permissions to a safe member, you are essentially defining the lifecycle of the secrets within that container by controlling which users or groups can perform specific operations. The most basic level of permission is list, which permits a user to identify the existence of objects within the safe without necessarily having the ability to view the credentials themselves. Moving up in complexity, the retrieve permission is what allows a user to actually display or copy the password, while the add permission allows users to inject new accounts into the safe for management. Update permissions grant the ability to modify account properties, and the delete permission allows the removal of accounts from the vault entirely, which should be restricted based on the principle of least privilege. It is vital to distinguish between functional, operational permissions, and administrative control, as mixing these roles often leads to compliance vulnerabilities. The managed safe member's permission is the most sensitive, as it allows a user to authorize other individuals to access the safe, effectively bypassing the security architects if not strictly monitored. You must be careful to distinguish this from the use permission, which is typically reserved for automated service accounts or specific application identities that need to authenticate to target systems without human intervention. When you configure an end user, such as a system administrator, you naturally lean toward providing retrieve and list, while keeping managed safe members reserved for the vault administrators or security officers. By separating these concerns, you ensure that no single individual has the ability to both manage the security structure of the vault and utilize the credentials stored within it, which is a standard requirement for proper auditing. One of the most consequential configurations you will encounter is the access without confirmation permission, which directly interacts with the dual control workflow settings defined in the master policy. When this checkbox is selected for a specific safe member, that individual is exempted from the standard workflow where an authorized approver must approve their access request before the credential is released. This permission effectively overrides the dual control mechanism for that specific user, regardless of what the broader policy might dictate for other users. While this provides necessary agility for emergency break glass scenarios or high-privilege service accounts, Utilizing it broadly invalidates the security objectives of having a dual control requirement. You should always maintain a clear mapping of which users hold this exception to ensure your audit trails accurately reflect why a specific user was capable of bypassing the standard request and approval lifecycle. The architecture of these permissions is inherently additive, meaning that if you assign a user to multiple groups that grant different levels of access to the same safe, that user will possess the sum of all permissions granted across those groups. When managing these assignments, always prefer group-based permissions over individual user assignments to keep your environment maintainable and easier to audit as your organizational structure shifts. If you find that a user needs restricted access, you can fine-tune their capabilities by unchecking specific permissions while keeping them as a member of the safe for broad visibility. Remember that these settings are local to the safe itself, which means you have the flexibility to define unique security parameters for every single safe in your Vault architecture. This inherent flexibility is a strength, but it requires diligent discipline in documenting your naming conventions and access patterns to avoid a disconnected and fragmented administration model. See you in the next lecture. Welcome back. In this chapter, we are going to explore the mechanics behind managing identities within the CyberArk Vault and how to bridge these identities with your existing enterprise directory services. Effective identity management is the bedrock of any privileged access management implementation, yet it often remains the most misunderstood aspect of the CyberArk ecosystem. When you master user management and LDAP integration, you gain the ability to scale your security posture automatically rather than manually provisioning every single account. This course is specifically designed to strip away the abstractions and provide you with a grounded, technical understanding of how to link your internal Vault security policies with external directory providers. You will learn to architect a robust identity strategy that reduces administrative overhead while strictly maintaining the principle of least privilege. If you are serious about passing the PAM-DEF exam and building a production-grade environment, this module is your essential guide to identity control. Managing users within the CyberArk Vault fundamentally requires a clear distinction between internal entities and external directory integrated accounts. Internal Vault users are purely managed within the CyberArk ecosystem, existing only inside the Vault's own database, which makes them ideal for emergency accounts or administrative users who must remain functional even if the corporate network experiences a total directory outage. Conversely, external LDAP users allow you to leverage your existing Active Directory infrastructure for authentication, thereby enforcing consistent password policies across your entire enterprise. The key to successful integration is recognizing that when you connect the Vault to your directory, you are not simply enabling users to log in. You are creating a structured mapping system that translates directory groups into logical Vault permissions. This synchronization process requires careful planning regarding which attributes are pulled from your domain controller, as these attributes inform the Vault about exactly who a user is and what they are permitted to do. When you configure directory mapping, you move beyond basic authentication and enter the realm of automated provisioning and lifecycle management. The Vault utilizes mapping rules to evaluate user attributes and map them to Vault groups, which in turn determines the user's effective permissions across different safes. These rules are processed in a specific order, meaning that if you have overlapping group memberships, the configuration's priority settings will dictate the outcome of the user's access profile. It is essential to understand that while the directory serves as the source of truth for user authentication and group membership, the Vault remains the owner of the authorization model. If you do not define precise mapping rules, you risk creating a security gap where unintended directory users inherit broad privileges simply because they reside in a specific organizational unit or security group. Testing these rules in a non-production environment is not just a recommendation. It is a necessity to ensure that your mapping logic aligns perfectly with your desired security reach. The impact of LDAP synchronization on user metadata and authentication flows is a critical, often overlooked technical detail. When a user first attempts to authenticate via LDAP, the CyberArk Vault does not immediately grant access, but instead checks its local database for a corresponding directory-mapped user entry. If the user is identified through your configured mapping rules, the Vault refreshes their group memberships based on the latest data from the directory provider, ensuring that access remains tightly coupled to current organizational structures. This behavior means that if a user is moved to a different department or removed from a privileged group in Active Directory, the vault will effectively revoke their access or adjust their permissions during the next authentication event. However, you must be aware of synchronization intervals and potential latency, as the vault does not query the directory for every single request once a session is established. Understanding this flow is vital for troubleshooting login issues, as authentication failures often stem from misaligned attributes or connectivity disruptions between the vault and the LDAP provider. Managing the lifecycle of these identities requires a pragmatic approach to how you handle internal versus external users. For standard domain users, relying on LDAP integration is the industry standard because it automates the onboarding process and ensures that password resets and account expirations are handled by the directory itself. For highly sensitive accounts, such as the master administrator or emergency breakdown accounts, you should exclusively use internal vault users that exist outside of your Active Directory environment. This approach creates a clean separation of concerns and adds a layer of resilience, ensuring that your core security infrastructure remains accessible even under severe directory-wide incidents. Always document your mapping rules and frequently audit the relationship between your directory structures and vault groups to prevent permission creep. By grounding your user management strategy in these established principles, you ensure that your vault remains both secure and highly maintainable as your organization grows. See you in the next lecture. Welcome to this chapter regarding the interaction with the Password Vault web access, which serves as the primary gateway for users to manage their credentials. We will examine how this interface functions, how to tailor it to your organizational requirements, and how to maintain the stability of the entire environment. The Password Vault Web Access, or PVWA, is more than just a simple browser-based front-end for the digital vault. It acts as the orchestration layer where users, administrators, and auditors interface with privileged account storage and session management capabilities. When you first log in, you are greeted by a dashboard that aggregates critical information about password vitality, pending requests, and general system health. Navigating this interface requires an understanding of the hierarchy of the underlying configuration settings. Administrators often find themselves spending a significant amount of time within the options menu, which is the centralized hub for all administrative adjustments. Being comfortable with these menus is a prerequisite for any defender tasked with maintaining a robust security posture within the CyberArk ecosystem. Organizations often require the interface to mirror their internal security and corporate branding policies to improve user adoption and trust. Within the Administration tab, you can modify elements such as the login header, footer, and the logo to ensure consistency with your internal portals. Beyond cosmetic adjustments, you have the granular ability to customize which tabs are visible to specific user groups based on their functional role. This concept of interface reduction minimizes complexity for end users, ensuring that they focus only on the tasks relevant to their specific permissions within the environment. Properly constraining the interface via these configuration options is an example of applying the principle of least privilege at the user experience layer. By creating bespoke workspaces, you effectively reduce the cognitive load for your team while simultaneously hardening the system against accidental misconfigurations. System health and monitoring are critical pillars of operational integrity, and the PVWA provides a dedicated dashboard to visualize these metrics. You should frequently utilize the system health pages to confirm the connectivity status of essential components like the Central Policy Manager and the Privileged Session Manager. These dashboards track communication heartbeat signals, ensuring that if a component fails to communicate with the vault, you receive an immediate indication of the service degradation. When inspecting these health screens, pay attention to the audit logs, as they often provide the diagnostic trail necessary to understand why a specific component might be flagged in a warning state. Maintaining constant surveillance of these health indicators is not just a routine task, but a defensive requirement to ensure your PAM solution remains highly available and functional. In an enterprise-grade deployment, high availability for the PVWA is typically achieved through load balancing and, occasionally, multiple instances distributed across a server farm. When configuring these environments, you must pay meticulous attention to the domain name system and the certificate lifecycle management. Because the PVWA relies on encrypted traffic via HTTPS, You need to import and bind trusted SSL certificates on your load balancers to ensure secure, uninterrupted communication between the client and the server. If the DNS configuration is not properly synchronized with the load balancer's virtual IP, users may experience intermittent access failures or certificate mismatch errors. Furthermore, the configuration files located on the web server must be kept in parity across all nodes to prevent inconsistent application behavior when a load balancer shifts traffic from one instance to another. See you in the next lesson. Welcome back, and let's dive into the core security mechanism that governs your entire CyberArk environment. In this session, we will examine the master policy as the primary baseline for your security posture and compliance enforcement. The master policy acts as the centralized authority for password management, defining the security requirements that propagate down to every platform within your CyberArk vault. When you configure the master policy, you are establishing the non-negotiable rules for password complexity, mandatory change intervals, and the frequency of verification. Think of this as the global constraint layer of a functional program. It sits at the top of the hierarchy to ensure that no platform resides outside of your organization's security baseline. By managing these rules centrally, you avoid the drift that inevitably occurs when configurations are siloed or managed sporadically across disparate platforms. It is the most robust way to enforce compliance, as it provides a single point of visibility for your auditors to evaluate how credentials are being lifecycle managed. Without a strong master policy, managing privileged access at scale becomes an exercise in configuration management hell, where the potential for error grows exponentially with every new onboarded account. Configuring these settings requires a firm grasp of how CyberArk translates high-level concepts into technical, actionable parameters. For instance, you will define how often the central policy manager initiates a password change, which is typically driven by compliance requirements for rotating secrets every 90 days or sooner. Beyond rotation, verifying that a password is still valid against the target resource is a critical function, as it prevents the situation where the vault hosts a secret that no longer works on the target system. When you look at password complexity, you are defining the character set allowed for the generated secrets, including length, numeric requirements, and special character inclusion, which must align with the target operating system's limitations. If you set a policy that requires passwords longer than what a specific legacy mainframe supports, you create a blocking issue that will prevent the CPM from successfully executing its management tasks. This is where the balance between security rigor and system interoperability becomes the primary focus of your daily operations as an administrator. In an ideal world, the master policy would apply to every object in your system, but reality often forces us to make concessions based on business unit requirements or unique technical limitations. This is handled by implementing exceptions, which allow you to override specific master policy rules for individual platforms or smaller scoped groups of accounts. An exception acts like a localized configuration that takes precedence over the global default, permitting you to relax a constraint when a specific legacy application simply cannot support it. However, you must track these deviations carefully, as every exception potentially represents a blind spot or a reduced security posture that might trigger an audit finding. When you decide to apply an exception, always document the underlying reasoning so that your security policy remains defensible rather than arbitrary. Managing these exceptions effectively is the difference between a secure environment that supports business velocity and one that is perpetually struggling against its own restrictive controls. When looking at the interface, you will see rules marked as either active or inactive, which allows for a granular level of control over how policies are enforced at any given moment. An active rule is currently being evaluated by the CPM to dictate account behavior, while an inactive rule exists in the system but carries no functional weight. This allows you to prepare security policies in advance, testing their impact or availability without affecting the live environment until you are ready to flip the switch. It can be useful to think of this in terms of state management. You are essentially toggling the enforcement state of your policy engine. By keeping rules inactive, you reduce the risk of accidental deployment, ensuring that your changes to the environment are intentional and verified. As you gain more experience, you will find that managing these states is essential for maintenance windows, especially when you need to pause enforcement for specific account types without modifying the underlying policy values. See you in the next module. Welcome to the module on platform management, where we delve into the fundamental configurations that dictate how your privileged accounts behave within the CyberArk ecosystem. This chapter is designed to bring you to the standard required to pass the PAM-DEF exam, ensuring you grasp the precise control mechanisms available for every managed object. In this chapter, we will explore the intricate world of platforms, which serve as the architectural bridge between your high-level master policy and the tangible behavior of individual accounts. We will examine the specific distinctions between target, RPC, and group platforms to ensure you can identify the correct tool for any given administrative requirement. By the end of this journey, you will be equipped to manipulate UI workflows, credential management cycles, and session recording parameters with confidence. Understanding these elements is not merely an academic exercise, as these configurations directly influence the security posture of your production environment. If you are serious about becoming a certified CyberArk professional, these concepts are non-negotiable building blocks for your success. We begin by establishing the role of platforms in the context of policy inheritance, which is a core concept that often surprises newcomers to the platform. While the master policy sets global compliance rules, it is the platform that allows you to override or refine these settings for specific sets of accounts or target systems. Think of the master policy as your organizational constitution, while the platform configuration acts as the specific case law applied to individual departments or machine types. This hierarchy is essential because it provides the flexibility to enforce stricter rotation policies on sensitive root accounts while maintaining standard intervals for regular service accounts. You must recognize that the platform is the primary mechanism for delegating governance to the object level, ensuring that your security controls are both granular and scalable. Without a firm grasp of how these settings cascade, managing a large-scale deployment becomes an exercise in manual intervention, which inevitably leads to configuration drift. It is vital to distinguish between the various platform types, starting with the target platform, which is assigned directly to an account to dictate how the central policy manager interacts with that specific resource. You will find that target platforms are the workhorses of the vault, handling everything from password complexity rules to the frequency of rotation and verification cycles. In contrast, RPC platforms exist primarily to facilitate remote password change mechanisms where target accounts interface with different operating system protocols or middleware. Group platforms add another layer of complexity by allowing you to aggregate accounts that share similar characteristics, enabling you to manage policies at a collective level rather than a singular one. Distinguishing these types allows you to troubleshoot connectivity issues effectively, as knowing whether an agent must be contacted via RPC or a standard agentless connection is fundamental to success. Mastering these definitions ensures you do not inadvertently apply an incompatible policy to a sensitive asset, which is a common scenario in the exam. Beyond the categorization, we must examine the internal architecture of platform settings, specifically focusing on the critical trinity of UI workflows, credentials management, and session management. The UI workflows section controls the interaction between the user and the password vault web access, determining what options are presented for account request and approval. Credentials management is the operational core, where you define exactly how the CPM generates, verifies, and rotates passwords according to your security requirements. Session management parameters define the limitations and observation levels for privileged sessions, including whether the privileged session manager will intercept the connection and what level of recording is required. These three areas form the configuration surface that you will manipulate to satisfy audit requirements and business continuity needs. Each setting within these categories has a ripple effect on the efficiency and security of your PAM deployment, making this depth of knowledge vital for any defender. As we transition into the specific settings, it becomes clear that platforms are not just static configurations, but active drivers of lifecycle enforcement. You will learn how the platform bridges the gap between the abstract master policy and the concrete reality of a password change transaction. When a discrepancy occurs, the platform settings are the first place you should look to see if a local override is masking a global policy or if an account is missing an expected behavior because it is assigned to an incorrect platform type. This relationship is deeply rooted in how CyberArk manages object metadata, and understanding it allows you to predict how the system will react to automated events. By controlling policy inheritance and overriding, You gain the ability to enforce compliance on a per-system basis, which is the hallmark of a mature PAM program. I look forward to exploring these nuances with you in the detailed modules that follow this introduction. See you in the next lecture. Hello. Let us look at the essential utilities and maintenance procedures required for a healthy vault environment. This chapter will equip you with the practical skills to manage services, monitor system logs, and execute backup strategies effectively. Working with a CyberArk Vault requires a solid understanding of its specialized administrative interfaces and command line utilities. The private Arc client serves as the primary administrative tool for managing the Vault's internal structure, allowing administrators to handle safe permissions, perform file management, and administer objects that might otherwise be invisible in the web interface. Beyond this, utilities like Export Vault Data, commonly referred to as EVD, provide a necessary bridge for security information and event management systems, as it allows you to extract metadata from the vault into a CSV or XML format for external auditing. This capability is pivotal for security teams who need to correlate privileged activity with external security events. Learning to navigate these utilities ensures that you are not just maintaining the system, but actively monitoring its integrity. When you master these tools, you move from being a user of the interface to a true custodian of the underlying security architecture. System stability relies heavily on your ability to control server services and monitor transactional data through standard administrative consoles. The Server Central Administration Console functions as the central dashboard for managing Vault services, providing the visibility needed to stop, start, or restart specific components without needing to interact with the underlying operating system directly. Equally significant is the constant monitoring of the IDLog file, which acts as the system's heartbeat. This file records all critical system events, from successful user authentications to failed login attempts and potential configuration errors, making it the first place an administrator should look when troubleshooting intermittent Vault behavior. While the Vault is designed for high availability and resilience, this record-keeping mechanism remains the most reliable source of truth during an audit or a proactive system health check. If you notice unexpected system behavior, cross-referencing these logs against your current configuration changes is the most efficient way to isolate a root cause. Managing the life cycle of data within the Vault necessitates a precise approach to backups and restoration procedures, especially when dealing with metadata and encrypted files. The Vault architecture relies on regular, encrypted backups of the private Arc environment to ensure that all safes, objects, and configurations can be restored in a disaster recovery scenario. You must distinguish between the Vault metadata, which tracks the structure and ownership of everything within the repositories, and the encrypted data files themselves, which contain the actual managed credentials. Failure to adequately protect the master key or the configuration files associated with these backups can render the data fundamentally inaccessible, even with the physical storage drives intact. During a restoration process, the synchronization between the backup metadata and the data blocks must be complete to maintain object integrity and avoid data corruption. This procedure is rarely a one-time setup and requires frequent testing to ensure that when a recovery is required, it is executed without error or data loss. See you in the next lesson. Hello, and welcome to this session on manual account onboarding within the CyberArk platform. In this chapter, we will master the techniques for bringing privileged accounts under administrative control via the Privileged Vault web access interface. When we approach manual onboarding, we are essentially defining the life cycle of a credential from the moment it enters the Vault. The process begins in the Password Vault Web Access, or PVWA, where you navigate to the account view to initiate the addition of a new account. This is not merely a data entry task. It is the establishment of a managed object that the central policy manager will eventually govern. You must select the appropriate safe to store the account, as the safe acts as the primary security boundary. Furthermore, you must assign a specific platform, which dictates the set of policies that govern how the password for that account is rotated, verified, or reconciled. Without a correctly associated platform, the account is effectively orphaned from a management perspective, leaving it outside the scope of automated compliance. During the manual addition process, providing accurate account properties is the most critical step to ensure future connectivity. You'll be prompted to enter the address, characterizing the target system and the username of the account you wish to manage. The password field is equally significant. You must input the current, valid credential that allows access to the target resource. If you provide an incorrect password here, the Central Policy Manager will fail its initial verification attempt, triggering an immediate notification or lockout depending on your policy configuration. It is a best practice to ensure the target system is reachable from the configured Central Policy Manager server before you commit these details to the vault. This initial verification serves as a sanity check to ensure that the account credentials are truly what you believe them to be. For environments where you need to onboard a higher volume of accounts than a single entry can handle, the PVWA offers a bulk import feature using CSV files. This utility is particularly effective for small to medium-scale migrations where you do not have the complex environment requirements for automated discovery. You download the standard template provided by the interface, which contains columns for all mandatory account properties, including the safe, platform ID, and target address. When you upload this CSV, the CyberArk system validates each row before creating the objects in the vault. This method mitigates the risk of human error associated with repetitive clicking in the web interface and ensures a standardized naming and property convention across your entire credential set. Always verify the status report generated after the import to confirm that every account was successfully provisioned in the required safes. Once you have manually added your accounts, whether individually or via bulk import, you must perform an immediate validation of connectivity. This validation is usually performed by triggering a manual verification operation from the account details page in the PVWA. By clicking the Verify button, you are instructing the Central Policy Manager to immediately authenticate against the target system using the newly stored credentials. This step is indispensable because it confirms that the Central Policy Manager has sufficient network permissions and correctly functioning credentials to manage the account lifecycle. If the connection fails, you are notified in real time, allowing you to rectify typos in the address or password immediately. Failing to test connectivity at this stage often leads to support friction later, when an automated password rotation fails in the middle of the night without clear remediation steps. Maintaining a rigorous approach to manual onboarding ensures that your PAM implementation remains clean and auditable. As you add accounts, keep in mind that every entry consumes resources and demands upkeep from the Central Policy Manager. By ensuring that each account is assigned to the most restrictive possible safe and the most appropriate platform, you are enforcing the principle of least privilege from the very first minute. This manual discipline prepares you for the more automated scenarios we will discuss later, where understanding the underlying properties remains just as vital. Remember that the vault is only as secure as the accuracy of the account metadata you provide during this onboarding phase. Consistency in how you represent an account's properties influences everything from the success of rotation policies to the precision of your eventual compliance reports. I will see you in the next lecture. Welcome to this session on automated discovery and dependency mapping. We will explore how to systematically identify and secure sensitive credentials throughout your IT environment. Managing a privileged account landscape manually is, frankly, an exercise in futility. As your infrastructure scales, the sheer volume of accounts across domain controllers, member servers, and various applications becomes impossible to track with spreadsheets or point-in-time audits. The CyberArk Discovery Engine exists to solve this by providing a continuous, automated mechanism to find accounts that have somehow escaped the boundaries of your governance model. You configure the Discovery Engine to scan specific IP ranges or organizational units, effectively shining a light into the dark corners of your network. When the scanner identifies accounts that meet your criteria, whether they are local administrative accounts or domain-level users, it populates the discovered accounts list within the Privileged Access Manager interface. This is not merely an inventory. It is the starting point for your onboarding strategy, allowing you to move accounts from an unmanaged, risky state into a protected vault environment with a few deliberate clicks. The mechanics of this scanning process rely heavily on the Central Policy Manager, specifically its scanning capabilities. When you define a discovery scan, you are essentially telling the CPM to reach out to target machines, authenticate, and enumerate the account metadata present on those endpoints. For local accounts, the scanner inspects the Security Account Manager database on Windows targets or equivalent repositories on Linux systems. For domain accounts, It observes active account usage within the Active Directory domain architecture. The goal here is to maintain a high-fidelity view of the privileged landscape without manual intervention. Because the environment is dynamic, regular scans ensure that shadow admins or newly created service accounts do not linger indefinitely without being brought under the security umbrella that the Vault provides. This visibility is the prerequisite for any meaningful enforcement. Perhaps more insidious than the accounts themselves are the dependencies lurking within your application stack. Many Windows services, scheduled tasks, and Internet Information Services application pools run under the context of a privileged account, sometimes hard-coded into configuration files or registry keys. If you rotate the password for such an account without accounting for these dependencies, you trigger a service outage, which is a catastrophic outcome in any production environment. The discovery engine assists here by identifying how these accounts are being consumed by system processes. By mapping these relationships, you create a safety net for your rotation policies. Before you force a password change, the metadata provides the necessary context to determine whether a service might break upon credential reconciliation. It allows you to transform your approach from reactive troubleshooting to a proactive stance where you update the account in the vault and simultaneously propagate that change to the underlying dependency. Understanding the distinction between discovery and onboarding is critical for the exam and for day-to-day operations. Discovering an account does not inherently mean it is secured. It simply registers the existence of a credential that satisfies your discovery criteria. You must then evaluate those results against your security standards to decide which should be moved to managed safes. When you onboard a discovered account, you associate it with a specific platform profile in the CPM. This platform determines the policy rules for password rotations, verification, and reconciliation. Only after successful onboarding does the vault assume control over the credential. Until that moment, the account technically remains at risk of compromise or misuse, regardless of how well it is identified within the discovery results. Always ensure your discovery scope is sufficiently narrow to be manageable, but broad enough to prevent gaps in oversight. See you in the next lecture. Welcome back. We are moving into the mechanics of automating your account lifecycle management within CyberArk. This chapter focuses specifically on the configuration and deployment of automatic onboarding rules to maintain a clean environment. In any reasonably sized enterprise, manually onboarding hundreds or thousands of privileged accounts is a recipe for operational failure. The automatic onboarding rules feature exists to move us away from this manual grind by enabling the system to ingest accounts discovered via the accounts feed based on defined business logic. When you think about this, consider the principle of least astonishment. You want the behavior of your automation to be predictable, transparent, and consistent across your infrastructure. If you leave discovery running without rules, you end up with a polluted vault filled with service accounts, local admins, and stale identities that nobody actually manages. Therefore, defining precise criteria is not just about convenience. It is a fundamental security control that prevents the sprawl of unmanaged privileged credentials within your environment. To implement these rules effectively, you must first have a clear understanding of the data being fed into the system by your discovery processes. The engine looks at specific attributes of the discovered accounts, such as the username pattern, the type of machine, or the operating system associated with the account. By defining these filters, you instruct CyberArk to ignore noise and focus only on the accounts that require management. For instance, you could configure a rule that targets all accounts starting with a specific prefix on your Windows Server fleet, while simultaneously excluding any accounts that reside on legacy staging machines. The logic follows a priority order, so the order in which you evaluate these filters matters significantly for the outcome. Once an account matches a criteria, the system needs to know where it belongs, which brings us to the necessity of mapping accounts to specific safes and platforms. The assignment of automatic safe and platform placement is the step where administrative efficiency meets granular security policy. You configure rules such that any account matching your filter is automatically dumped into a designated safe, which inherently possesses the appropriate access controls defined by its members. Simultaneously, assigning the correct platform, such as a Windows domain account platform or a Unix SSH key platform, ensures that the central policy manager immediately identifies how to interact with the password object. This automation reduces the administrative overhead of manual onboarding but it also enforces a standardized management posture on every new account that enters the scope. Without this systematic placement, you would inevitably end up with platform configuration drift, where accounts meant for the same group end up being managed by different or perhaps less secure policy settings. Before you activate these rules in a production environment, you must perform rigorous testing of your rule logic. An improperly configured rule can lead to unauthorized account sprawl, where service accounts that should stay in a specific isolation zone are suddenly moved into high privilege management. Safes, potentially creating security risks or breaking existing application dependencies. Always use the test functionality provided in the interface to simulate the onboarding process against existing discovered accounts. This allows you to verify that the filters you have constructed are hitting the correct accounts and that the assignment logic is pushing them to the appropriate destination. Think of this as your safety net. It validates that your intended business logic translates correctly into the system's execution path before the rule becomes operational. As you refine these rules, consider that your infrastructure is likely a living, breathing entity that changes over time. Your naming conventions might evolve, new server roles might be introduced, or business units might change their directory service structure. Consequently, automatic onboarding rules are not a set-it-and-forget-it component of your architecture, but rather a configuration subject to periodic review. When you audit your environment, look at the accounts currently in your discovery feed that have not been picked up by any rule. If you see a cluster of relevant accounts being ignored, it is a signal that your rules need to be updated to account for new naming conventions or organizational changes. By keeping these rules current, you maintain the rigor of your privileged access security program rather than allowing it to decay into a collection of undocumented manual exceptions. I will see you in the next lecture. Welcome back again as we transition from manual onboarding processes into the more scalable realm of programmatic interactions with the CyberArk Vault. In this session, we will focus on how REST API capabilities act as a force multiplier for managing sensitive credentials across complex infrastructures. When we move beyond the graphical interface, we enter an environment where the CyberArk REST API becomes the primary interface for identity management. The API provides a structured, programmatic way to interact with the Vault, allowing you to treat your security infrastructure as code rather than a collection of static tasks. For anyone operating within CI/CD pipelines or managing ephemeral cloud-native environments, manual intervention is simply not a sustainable strategy. By leveraging the REST API, you can ensure consistent, reproducible configurations for safe creation and account onboarding that scale alongside your deployment targets. This shift in perspective allows you to embed security deeply within your automation workflows, reducing the friction that often leads to configuration drift or human error. Ultimately, the API is not just a convenience, it is a fundamental requirement for modern DevSecOps practices. To interact with the CyberArk API, we must first establish a secure session, which requires a robust authentication mechanism. The API typically employs a session-based authentication flow where you authenticate against the REST service using your credentials or a PKI certificate. Once you authenticate, the service returns a session token, which you must include in the header of all subsequent requests to prove your identity. It is crucial to handle these tokens with extreme care, as they represent privileged access to sensitive vault operations. Once authenticated, we can target core endpoints that allow us to perform administrative tasks, such as creating new safes to house accounts, or adding specific objects to those containers. Mapping out your infrastructure in JSON format is the standard here. So providing accurately structured request bodies is essential for the system to interpret your intentions correctly. Understanding the anatomy of these JSON requests is where precision becomes paramount for success. When you initiate a request to add an account or create a safe, the structure of your JSON object must strictly adhere to the schema expected by the Vault. A typical account onboarding request will require specific fields such as the address of the target machine, the username, and the associated platform ID. If you fail to include a mandatory field or misalign a nested object within your structure, the API will return a 400-level error, forcing you to diagnostic steps. By mastering these structures, you ensure that your scripts function predictably, whether you are onboarding a single batch of credentials or synchronizing thousands of accounts during a cloud migration. Consistency in your JSON payload design is the hallmark of a mature automated onboarding process. The strategic benefit of this programmatic approach is most visible when integrating into CI/CD pipelines. Every time a new service is deployed in a cloud environment, you can trigger an API call to create a dedicated safe and register the service account's credentials automatically. This removes the wait time associated with manual request processing and ensures that security policies are enforced from the very first minute of the lifecycle. By automating the registration of dependencies, you create a seamless chain of trust that starts from the infrastructure provisioning layer and extends into the credential management layer. As you become proficient with these endpoints, you will find that the vault effectively disappears into the background of your deployment process. This is the goal of a well-integrated PAM solution within a high-velocity engineering organization. See you in the next lecture. Welcome back. We are now entering the thick of things by examining how CyberArk manages various types of privileged accounts across your infrastructure. In this session, we will dissect the technical nuances of handling local and domain accounts alongside more specialized targets like database users and cloud identities. Managing accounts effectively requires a firm understanding of what actually constitutes the link between the CyberArk Central Policy Manager and the target system. When we talk about Windows domain accounts, we are essentially looking at objects living within Active Directory, where password management relies on standard Kerberos or NTLM traffic and appropriate permission sets for the CPM user. Conversely, local Windows accounts exist strictly within the Security Accounts Manager of individual servers, requiring the CPM to possess sufficient local administrative rights to modify credentials. The key architectural distinction here is the scope of control, as domain accounts often require synchronized changes across domain controllers, whereas local accounts are isolated and therefore immune to broader domain policy conflicts, but vulnerable to individual system availability issues. You must ensure that the CPM platform is configured with the correct administrative credentials to perform these distinct operations, or the password management cycle will perpetually fail. Moving into the world of Unix and Linux, the management paradigm shifts toward SSH-based communication rather than the RPC mechanisms used by Windows systems. CyberArk handles these by leveraging the SSH protocol, where the CPM connects to the target and executes commands to rotate the password or verify existence. You will find that these platforms require careful attention to the SSH keys or passwords used for the management session, as well as the specific command syntax defined in the platform configuration. If the Linux environment is locked down with strict sudo or file constraints, the CPM process might struggle unless it has the privilege to perform the necessary password updates without hitting interactive prompts that break the automated workflow. Understanding the target platform's shell environment and the underlying security restrictions is paramount for maintaining consistent account health in a Unix-heavy estate. Complexity increases significantly when we pivot to database users and cloud IAM roles, which behave quite differently from traditional operating system accounts. For SQL or Oracle databases, CyberArk needs to establish a direct connection to the database engine, meaning the CPM host must have the necessary database drivers installed and accessible. You are not just updating a credential, but often interacting with an application-specific security layer that might enforce its own complexity rules and lockout policies that conflict with the Vault's settings. With cloud IAM, such as AWS or Azure roles, you are typically managing secrets, tokens, or API keys rather than a standard system password. These cloud resources often necessitate communication over HTTPS, and the account properties must accurately reflect the specific API requirements or tenant identifiers needed to authenticate the management request through the cloud provider's front door. Differences in connection parameters are not merely a technical annoyance, but a fundamental aspect of how the Vault ensures security through the principle of least privilege. Each platform type within the CyberArk interface carries a specific set of properties and parameters that dictate how communication happens, from the specific ports in use down to the command execution patterns. If you misconfigure the logon account or the reconciliation account associations for a specific database or cloud object, you will quickly find that the CPM cannot complete the password rotation cycle. It is worth remembering that the platform itself acts as a blueprint for these interactions, and tweaking properties like timeouts, retry limits, or specific management scripts for unique legacy systems is a standard part of the administrator's workload. Focus on the platform-specific requirements for each resource type, and you will maintain a much higher success rate in your automated account lifecycle management. I look forward to discussing the next steps in your configuration journey in our next session. Welcome back. In this session, we will examine the technical mechanics of securing non-human identities using credential files and the specific practices required for maintaining service account availability. When we deploy CyberArk components, such as the Central Policy Manager or the Privileged Session Manager, we face a fundamental bootstrapping problem. How does an automated service authenticate against the vault without hard-coding passwords and configuration files? The answer lies in the use of credential files, often identified by the CRED extension, which act as encrypted, location-bound security artifacts. The Create CRED file utility is the standard tool provided by CyberArk to generate these files. When you execute this utility, you are essentially creating a secure wrapper around the authentication credentials that the component needs to establish its initial connection to the vault. It is important to remember that these files are tied to the machine's identity and the specific user context running the service, which prevents them from being easily copied and misused on unauthorized servers. By abstracting the password away from plain text configuration files, we enforce a principle of least privilege at the infrastructure layer, ensuring that even if a configuration file is read, the underlying vault password remains shrouded. Managing service accounts within the vault introduces a distinct set of operational challenges, particularly because these accounts often perform mission-critical tasks that cannot tolerate downtime. Unlike human users who can manually update passwords after a rotation failure, automated processes fail immediately if their credentials desynchronize. We mitigate this by utilizing the vault's ability to store and manage these credentials directly, while the components retrieve them via secure, authenticated channels. When configuring service accounts, you must ensure that the associated platforms are configured to track dependencies, allowing the Central Policy Manager to track all downstream services that rely on a specific account. This visibility prevents accidental breakage during automated password rotations, as the system can verify if a change will impact a verified service dependency. By maintaining this inventory, we transition from reactive troubleshooting to proactive lifecycle management of non-human identities. The actual rotation of credentials for service accounts is a delicate operation that requires careful coordination between policy settings and the environment. You should always leverage the Vault's native capability to perform account verification prior to a password change, ensuring that the account is currently functional before the system attempts to update it. If a rotation fails, the Vault provides granular audit logs that pinpoint exactly which process or service encountered the authentication failure, allowing for rapid remediation. When we manage these identities, we also focus on the concept of exclusive locking, which prevents multiple processes from trying to rotate or use the same credentials simultaneously, an event that would almost certainly cause an architectural outage. Implementing a robust rotation policy requires you to understand the balance between security, which demands frequent changes, and availability, which demands consistency. Therefore, your configuration should reflect the specific risk profile of the application or service being managed. Ultimately, the goal is to eliminate static, long-lived passwords from your environment, replacing them with dynamic, vault-managed credentials that are automatically rotated and audited. Even for legacy systems that do not natively support API-based credential retrieval, the use of credential files provides a secure bridge that integrates these systems into the broader CyberArk security umbrella. By mastering the command line arguments of the Create CRED file utility and understanding how the Central Policy Manager triggers rotations based on defined policies, you ensure that service account management does not become a manual burden. Keep in mind that securing these non-human identities is often more critical than managing human admin accounts, as service accounts frequently possess broad, persistent access across the network. If these accounts are compromised or their rotation fails, the resulting impact can be significant. So testing your rotation policies in a non-production environment remains a prerequisite for any enterprise-grade deployment. I will see you in the next lecture. Welcome back. In this session, we will examine the complexities of managing service account dependencies during credential rotation. When we onboard a service account into the CyberArk Vault, we are rarely dealing with a single, isolated entity. Most technical environments rely on service accounts that are hard-coded into Windows services, scheduled tasks, and various application pools. If the Central Policy Manager rotates the password for the primary account, but fails to propagate those changes to the associated services, the inevitable result is a service outage. The architecture of the central policy manager provides specific functionality to handle these dependencies, but it requires careful configuration of the platform settings to function as intended. You must treat these dependencies as active components of the account lifecycle rather than static metadata. Failure to synchronize the change process with these underlying service dependencies will lead to failed password verifications and service downtime. To manage these dependencies effectively, we utilize the capability of the CPM to automatically detect and update services that are linked to the managed account. When the CPM performs a password change, it can be instructed to perform subsequent actions on specific machines where the dependent services reside. This process relies on the target account having the appropriate permissions to stop and start services on the target server. If the account lacks the required privileges, the dependency update will fail, even if the primary password change in the vault succeeds. You need to ensure that the account designated for the CPM operations has the necessary service control manager rights on the remote Windows machines. This often involves ensuring the account is a member of the local administrators group or has been granted specific service management permissions via group policy objects. The management of Internet Information Services application pools is a distinct challenge compared to traditional Windows services. When a password changes, the application pool identity must be updated and the process recycled for the new credentials to take effect. If you do not configure the dependency management properly, the application pool will continue to run with the stale credential until someone manually restarts it. In a high availability environment, this could create unpredictable results, especially if the service crashes upon the next recycling event. The CPM handles this through specific plugin configurations that target the IIS metabase to update the identity password. Always test these configurations in a non-production environment before moving to your live infrastructure to ensure the recycle operation does not cause unexpected session loss. Complex applications present a unique category of dependency because they operate within the context of DCOM and often require specific interaction with the Component Services Management Console. When an account running a COM+ application is rotated, the credentials must be updated within the COM+ catalog, which is quite different from simply updating a service or a scheduled task. The CPM requires specialized platform parameters to correctly interact with the component object model settings. If the update is not handled correctly, the COM+ server application may fail to activate on subsequent requests. This is particularly sensitive in enterprise applications where COCAM+ components facilitate critical middleware communications. A thorough understanding of how your specific middleware utilizes these accounts is mandatory before attempting to automate their password lifecycle. Validating the success of these operations is the final and most critical phase of your task. It is not enough for the vault to report that the password change was successful. You must verify that the services have restarted and are currently running with the new profile. This involves reviewing the CPM logs, which detail every step of the dependency refresh, including the specific commands issued to the service control manager. If a service remains in a stop state or fails to start, the log will indicate the specific error code returned by the Windows operating system. Analyzing these error codes allows you to move beyond generic troubleshooting and address the root cause, which is often a permission issue or a dependency conflict that was not accounted for during the initial onboarding. Maintaining operational uptime depends on this verification logic being proactive rather than reactive. See you in our next lecture. Welcome back. In this lecture, we will explore the mechanisms for mass account onboarding into the CyberArk Vault using bulk utilities. When we transition from legacy password management systems, or perhaps when we are initializing a fresh environment, the manual creation of accounts through the Privileged Vault web access interface quickly becomes impractical. The sheer scale of modern enterprise deployments often necessitates the migration of thousands of accounts, making manual entry a bottleneck that also introduces significant risk through human error. CyberArk provides professional-grade tools for this purpose, specifically the Accounts Upload utility and the bulk import functions found within the PVWA. These utilities are designed to streamline the migration process by allowing administrators to define account properties in a structured data format, which the Vault then ingests. Understanding the internal mechanics of these tools is not merely about mechanical proficiency. It is about grasping how the Vault imposes schema constraints on incoming data to ensure that every managed account remains secure and compliant from the moment of ingestion. The primary interface for this operation is the CSV-based import mechanism, which requires meticulous attention to the structure of your source data. CyberArk utilities rely on specific column headers and strict formatting rules to map your external data into the corresponding safe and platform attributes within the vault. If you fail to map a field correctly, for example, if you provide an improperly formatted date or an invalid platform ID, the utility will reject the entire row or, in some cases, fail the entire batch. You must normalize your data before attempting an upload, ensuring that parameters such as address, username, platform type, and safe name are validated against the target environment. I suggest you approach this by performing a small-scale trial run with a limited subset of accounts before broad-scale automation, as the cost of cleaning up an incorrectly populated vault can be significantly higher than the time spent on proper data preparation and validation. Handling errors during these bulk operations is an unavoidable reality of large-scale environment engineering. When you initiate an upload, the utility generates log files that detail either the success or the specific cause of failure for each account record. You should treat these logs as your primary feedback loop. They frequently point to permission issues on the destination's safe, missing platform policies, or syntax errors within your source file. It is common to encounter issues where a specific account might fail a validation check against the master policy. In such scenarios, the utility will report that the account is incompatible with the specified policy settings. Rather than force-fitting accounts, examine the policy constraints enforced by the CPM, as this will help you determine whether the account requires a different policy or if the existing policy needs adjustment to accommodate the new credentials. Migrating accounts at a massive scale requires a clear strategy that balances import speed with system stability. When dealing with thousands of credentials, you are essentially asking the vault to perform thousands of concurrent writes, which can put a significant load on the vault server and the associated CPMs responsible for those new accounts. I recommend staggering your imports into manageable batches rather than overwhelming the system with a single monolithic file. This approach allows you to verify that the vault and the CPM are successfully performing initial password verifications on these new objects as they are brought under management. By breaking the work into logical groupings, you also gain the ability to monitor the performance of your infrastructure, confirming that your vault architecture can handle the provisioning load without negatively impacting existing privileged session management or password rotation tasks. The logic within these utilities reflects the fundamental way CyberArk handles account lifecycle management, where the identity of the account is inextricably linked to the platform policy that governs it. Ensuring that your metadata is clean and your mappings are precise is the difference between a seamless onboarding project and a series of technical hurdles that delay your security objectives. As you get hands-on with these utilities, you will observe that the bulk import functionality is less about mass storage and more about ensuring that every account, from the first to the 10,000th, inherits the security posture of your organization's established policy framework. Proper planning of your source data structure, coupled with cautious, batch-oriented execution, will ensure that your onboarding objectives are met with both precision and high availability. See you in the next lecture. Welcome back. Today we are going to dive deep into the operational mechanics of the Central Policy Manager and how it handles credential lifecycle events. The Central Policy Manager is the engine that facilitates the automation of high-privilege credential management within the CyberArk ecosystem. When we talk about change and verification, we are essentially discussing the state synchronization between what the vault stores and what the target system actually recognizes. Verification is the process where the CPM proactively checks if the password managed in the vault matches the password currently residing on the target account. This process is crucial because it ensures that our administrative records remain accurate without requiring immediate password rotation. If the CPM detects a mismatch during a verification cycle, it does not necessarily trigger a password change. Instead, it logs the discrepancy and alerts the system, allowing administrators to investigate potential unauthorized changes to the target account. This logic relies heavily on the platform-specific settings that define how often these checks occur and what the CPM should do when it encounters an inconsistency in the managed environment. The change process is the more aggressive counterpart to verification, designed to refresh secrets according to the security policies defined in the master policy or platform-specific settings. When a change is triggered, the CPM generates a new password based on the complexity rules defined in the platform configuration and attempts to push this new credential to the target device. This transition is not always linear, as the CPM must first successfully authenticate to the target using the existing credentials stored in the vault before it can apply the change. Once authentication is successful, the CPM executes the password change command, updates the remote target, and then verifies that the new password is functional. Only after this verification, confirming the success of the update, does the CPM store the new, verified secret within the vault. This sequence ensures that the vault never contains a credential that cannot actually be used to access the target system, effectively preventing locked-out accounts. Triggers for these automatic actions are governed by the platform policy settings, which dictate the frequency and conditions under which the CPM intervenes. We often set these intervals based on regulatory compliance requirements or organizational security standards that mandate frequent password rotation for administrative accounts. For instance, a system might be configured to verify that a password remains consistent every 24 hours, while also mandating an automated change cycle every 30 days. The CPM parses these rules, maintains its own internal schedule for every managed account, and triggers actions based on the password change and verification parameters. If an account is marked as exclusive or requires immediate rotation due to a security incident, these automated triggers can be overridden by manual intervention from an authorized user. The CPM constantly polls the vault for these tasks, ensuring that policy enforcement remains continuous and independent of human manual intervention. It is important to understand that the CPM does not act in a vacuum, but relies on the platform's connection component to bridge the gap to the end target. If a platform is misconfigured, or if the communication channel between the CPM and the target is restricted, the verification and change cycles will fail, leading to an aging out of the credential. In such a scenario, the CPM will typically retry the operation based on the failure management settings defined in the policy, such as the maximum number of retries or the delay between consecutive attempts. These settings exist to prevent the account from becoming locked on the target system due to rapid-fire failed authentication attempts, which is a common defense mechanism on many operating systems and databases. By fine-tuning these settings, you ensure that the CPM remains efficient and responsive without causing unintended service disruptions to your managed infrastructure. As you continue to explore the operational side of the platform, remember that the logic behind these processes is exactly what allows for enterprise-scale privileged account management. The reliability of the entire PAM solution rests on the predictability of these cycles and your ability to monitor them through the vault logs and the PVWA interface. When you configure a new platform, you are essentially defining the behavioral boundaries of the CPM. And this is where most errors in production environments originate. Always ensure that the policies you assign to your safes and accounts align perfectly with the operational requirements of the target platforms you are managing. Taking the time to understand these verification and change mechanics now will save you from significant troubleshooting efforts later in your operational workflows. See you in the next session. Welcome to this chapter on reconciliation and emergency access, where we will navigate the mechanisms required to maintain credential integrity when standard rotation fails. By the end of this module, you will have a deep understanding of how to restore access without compromising the security posture of your environment. In an ideal world, the central policy manager would always successfully log in to a target system and update a password. However, in reality, credentials fall out of sync for various reasons, such as manual changes made locally or system updates that interrupt automated processes. The reconcile account, or reconciliation account, is the specific privileged identity configured within CyberArk to resolve these discrepancies by overriding existing credentials. It must be an account with broad permissions, typically a domain administrator or an equivalent local user, capable of resetting passwords for a defined set of target accounts. It exists as a distinct entry in the vault that your platform policies reference whenever the standard change process reports a failure or an inability to authenticate. Configuring this functionality happens at both the platform level and the specific account level, allowing for a granular security model. At the platform level, you associate a particular account as the reconcile account for an entire class of systems. This ensures that every account managed by that platform has a designated recovery path by default. If you need a more specific override, you can specify a unique reconcile account at the individual account level, which takes precedence over the platform setting. This is particularly useful in environments where organizational units or specific server groups require higher privileged accounts than those defined in the broad policy. Once associated, the internal CPM logic tracks the history of synchronization failures and determines when to invoke this recovery mechanism. When a password becomes truly unknown or an account is fundamentally out of sync, the reconcile process acts as a fail-safe. The CPM, recognizing that it cannot verify the current password, switches logic to use the reconcile account to log into the target system. It performs a password reset operation directly, effectively discarding the previous unknown value. This is a powerful feature, but it requires that your reconcile account has the reset password permission on the target system. Because of the inherent risk in having an account capable of overriding any sensitive credential, you must treat the reconcile account itself with the highest level of security. It must be subject to rigorous auditing and should frequently rotate its own credentials via the same or even more robust policy settings. The reset on next access workflow is another critical component that relies heavily on these reconciliation permissions. When a user requests a session through the Password Vault web access and the system detects that the password might be stale, it can trigger a reset immediately before granting access. This ensures that the user is always presented with a fresh, verified credential while maintaining non-repudiation and accountability. This feature effectively bridges the gap between automated background maintenance and user-initiated access, minimizing the window of exposure for static passwords. For this workflow to function reliably, your environment must guarantee that the reconciliation path is correctly mapped and that the reconcile account is active and authorized. If the mapping is missing or the permissions are insufficient, both manual and automated recovery workflows will fail, leaving the account inaccessible and potentially requiring human intervention. See you in the next lecture. Welcome back. In this session, we will examine the mechanics of platform management and tweaking to refine how your environment interacts with target systems. When you manage privileged accounts at scale, you will inevitably find that the default platform settings crafted by CyberArk do not align perfectly with every specific technical requirement within your infrastructure. The platform essentially acts as a set of instructions for the Central Policy Manager, or CPM, defining how it should connect to, manage, and verify accounts. Instead of attempting to modify the out-of-the-box platforms, which can lead to confusion and unintended side effects, the established best practice is to clone an existing platform. You take a functional template, create a copy, and then apply your specialized adjustments to that new instance. This process ensures that you maintain a clear audit trail of your customizations while keeping the original default platforms in a clean, pristine state for future reference. Once you have a cloned platform, you gain granular control over the behavior of the CPM for those specific target accounts. One of the most critical aspects of this tuning involves adjusting the search and update intervals, which determine how aggressively the CPM interacts with your systems. If a specific system requires more frequent verification, or if a legacy device struggles under the load of constant connection attempts, you can modify these intervals within the platform settings. The search interval dictates how often the CPM scans for accounts that are due for a password change, while the update interval governs the timing of the actual policy execution. By finding the right balance here, you prevent the CPM from becoming a bottleneck while ensuring that your compliance requirements for periodic rotation are strictly maintained. It is a matter of knowing your environment's capacity and aligning the CPM performance features to match your specific operational overhead and system sensitivity. Beyond timing, you often need to configure notification settings, especially when dealing with failed password management operations. When an automated task fails, it is not enough to simply hope that someone notices the discrepancy in the vault logs. You want proactive alerts that notify the appropriate administrators immediately. By adjusting the notification settings within your custom platform, you can ensure that the system triggers specific emails or SNMP traps whenever a change or verification operation ends in an error. This level of configuration allows you to define who needs to be contacted when a platform-specific issue arises, which significantly reduces the mean time to repair for managed accounts. It shifts your security posture from a reactive state to a more resilient, well-monitored environment where failures are visible and actionable. You must also be diligent in managing the automatic management flags, which dictate whether a password is actively being managed by the CPM or if it is currently in a manual override state. Sometimes, you may need to temporarily pause automatic management for troubleshooting purposes without deleting the account association or altering the platform policy itself. By toggling these flags, you control the operational state of the account, ensuring that the CPM does not attempt to rotate a password while a system administrator is performing a manual task that requires the password to remain static. This is a powerful feature that requires disciplined use, as leaving an account in a disabled state indefinitely can easily lead to compliance gaps if it is forgotten. Always ensure that your internal process mandates a verification step to re-enable automated management as soon as the manual intervention is complete. Deep within these platforms, you will find that specific settings are capable of overriding the global defaults defined in the master policy. The master policy is your overarching compliance framework, but platform-level overrides allow you to carve out exceptions for systems that simply behave differently due to technical debt or unique access requirements. For example, if your master policy mandates a password change every 30 days, but you have a specialized legacy application that relies on a hard-coded secret in a remote binary, the platform override provides a mechanism to handle that edge case safely. You are essentially telling the vault that for this specific set of accounts, the standard rule must yield to the platform's localized configuration. This hierarchical approach to policy application ensures that your security standards remain robust enough for 95% of your infrastructure, while still remaining flexible enough to support the reality of complex enterprise architectures. See you in our next exploration of how these components work together. Welcome back. We are moving into the mechanics of exclusive access and automated rotation. When we talk about securing privileged credentials, we often face a trade-off between accessibility and strict security control. In many environments, having multiple administrators sharing a single account password creates a significant accountability gap, as it becomes impossible to determine who performed a specific change. CyberArk addresses this by implementing an exclusive check-in and check-out mechanism that ensures only one user can access a credential at any given time. When a user requests an account that has been configured for exclusive access, the central policy manager places a lock on that object within the vault. This prevents any other user from retrieving or using the password until the first user has finished their session and checked the account back in. It is a fundamental operational pattern that transforms a static password into a controlled, single-threaded resource. The checkout process is fundamentally managed by the PVWA interface, where a user explicitly requests access to a platform-managed account. Once the request is approved, if dual control is also enabled, the account becomes locked for that specific user. From this point forward, the CPM marks the account as unavailable for any concurrent sessions or automatic password changes that might be scheduled. This locking mechanism is essential because if the CPM attempted a password rotation while a user was mid-session, that user would be immediately disconnected and potentially lose their work. By enforcing exclusivity, we align the technical state of the account with the human workflow, ensuring that the password remains static and valid for the duration of the approved access window. Once the session is concluded, the user must check the password back into the vault to release the lock. This is where we often layer in the one-time password strategy to further harden the administrative environment. If you configure a platform to use one-time passwords, the system is instructed to perform an immediate password change as soon as the account is checked back in. This effectively makes every single use of an account completely unique. Even if a user were to capture the password during their session, that secret would be rendered useless milliseconds after they relinquish the lock. The CPM identifies the check-in event as a trigger to initiate the password change process, ensuring that the next person to request the account receives a fresh, unknown credential. Configuring this behavior requires a precise understanding of the platform settings within the PVWA. You must navigate to the specific platform and enable the enforced check-in/checkout setting, which essentially tells the system to track ownership of that credential object in the vault. If you pair this with immediate password rotation, You are essentially reducing the risk of credential leakage to the absolute theoretical minimum. Keep in mind that this introduces a slight overhead for the CPM server, as it must now manage a higher frequency of password change requests compared to a standard daily or weekly rotation cycle. You should evaluate the performance of your CPM scanning intervals to ensure that these immediate change requests are not queued behind long-running reconciliation tasks. The interplay between the manual check-in process and the CPM operation is where many administrators encounter unexpected friction. If a user does not properly check the account back in, the account remains locked, and the CPM cannot proceed with the requested password change. You may need to design operational procedures or scripts that handle these exceptions, perhaps utilizing authorized users who can release locked accounts if an administrator leaves the organization unexpectedly. However, the system is designed to prefer safety over availability, meaning it will refuse to rotate a password while a lock is active. By mastering these platform policies, you create a dynamic, self-defending architecture that anticipates the needs of your privileged users while maintaining a rigid audit trail. I will see you in the next installment. Welcome back to the course, where today we focus on implementing dual control and managing the critical request workflows within the Vault. In this session, we will examine the mechanics of access confirmation, commonly referred to as dual control, and how it enforces a rigid separation of duties within your privileged account management strategy. By requiring a second set of eyes on every checkout request, you ensure that no single administrator can gain access to highly sensitive credentials without explicit authorization. We will break down the life cycle of these requests, covering the entire flow from the moment an end user creates a request until the final outcome of approval or denial. Security architects often overcomplicate this process, but at its core, it is simply a state machine that governs how your environment handles high-impact access requests. Understanding these states, creating a request, the approval phase, the subsequent use of the account, and the potential denial is fundamental to passing your certification. We will also touch upon the necessity of defining specific authorized approvers who act as the gatekeepers for your safes. This configuration ensures that access is never arbitrary, but rather a deliberate administrative decision that is tracked and audited at every single step of the process. When you configure access confirmation, you are essentially modifying the security parameters of a safe to require an explicit administrative handshake before a password is released. This feature is not a global toggle, but rather a setting applied at the safe level, allowing you to implement granular control policies based on your organization's specific risk tolerance for different asset tiers. Once enabled, the standard behavior of clicking Connect or Show Password changes, forcing the CyberArk PVWA to intercept the request and route it to configured approvers. You must designate specific users or groups as authorized approvers for that particular safe, and these individuals receive notifications via the PVWA dashboard to review the pending request. Failing to define these approvers properly means that requests will linger in an indeterminate state, effectively locking down the account until an administrator addresses the backlog. This hierarchy of authority is the primary defense against internal abuse, ensuring that even a privileged account holder lacks the unchecked capability to access production credentials. The life cycle of an access request follows a serialized path that maintains an unbreakable audit trail, which is why organizations heavily reliant on compliance standards lean so hard on this functionality. A user initiates the request by selecting the target account and providing a justification, which is then serialized and recorded in the Vault's database as a formal entry. The request status transitions to pending, triggering notifications to defined approvers who evaluate the validity of the request against documented internal policies. If an approver denies the request, the workflow terminates, and the user is prevented from seeing the credential, maintaining the hardened posture of your Vault. Upon approval, the status changes to authorized, granting the requester a window of time, usually configurable, during which they can perform their intended session or retrieve the password. Once the time limit expires or the usage is completed, the request is finalized and archived, providing auditors with a verifiable history of who requested access, who authorized it, and exactly when the usage occurred. Beyond the native interface, dual control is designed to integrate seamlessly with external enterprise ticketing systems like ServiceNow or Jira, which is a major focus for production-grade security architectures. This integration allows the CyberArk Vault to cross-reference a pending request against a valid, open ticket number, ensuring that high-privilege access is tied directly to a legitimate business requirement or maintenance task. When this workflow is automated, the Vault validates the ticket status through a REST API call, and if the ticket is not in an in progress or approved state, the access request is automatically rejected. This architectural choice effectively eliminates the human element of manual checking and ensures that audit logs in CyberArk perfectly match the audit logs in your IT service management platform. By enforcing this verification, you transform the Vault from a simple password repository into a proactive compliance engine that actively blocks unauthorized activity before a credential is leaked. It is a powerful pattern that ensures every single privileged operation is accounted for, creating the kind of defensible security perimeter that auditors look for in a PAM maturity assessment. See you in the next lesson. Welcome back to our exploration of the CyberArk platform. In this session, we will discuss how to enforce accountability by integrating the Password Vault web access with external ticketing systems. When we manage privileged accounts, the primary goal is often to establish a clear link between a deliberate administrative action and an authorized change request. By configuring the Password Vault web access to require a valid ticket ID before permitting a user to retrieve a password or launch a session, we bridge the gap between operational tasks and IT service management. This workflow ensures that no privileged activity occurs in a vacuum, as the system acts as a gatekeeper that demands an external reference. Within the platform, you can configure these requirements at the platform level, which effectively dictates the behavior for every account managed under that specific policy. This is not merely an optional feature, it is a fundamental control for organizations that must adhere to strict audit requirements like SOX or PCI DSS. By forcing this explicit link, you create a trail of accountability that is easily verifiable by external auditors who need to see the justification for every password checkout. The actual validation logic can vary depending on your organizational needs and the capabilities of your ticketing platform. At the simplest level, you can implement validation using regular expressions, which effectively forces users to enter a string that matches the expected format of, for example, a ServiceNow incident number or a Jira issue key. While regex validation is an excellent way to prevent basic input errors or casual abuse, it does not verify that the ticket actually exists or that it currently resides in an open state. For a more robust implementation, you might configure the system to perform real-time verification against the ticketing system's API. This approach requires that the PVWA has clear network connectivity to the ticketing server and the appropriate credentials to query the service for status updates. When configured this way, the user input is validated not just for syntax, but for semantic correctness against your live ecosystem. Once a request has been made and a ticket ID has been provided, the compliance auditing becomes significantly more valuable for the security team. Every entry in the audit log will now map directly to a business process object, allowing you to filter session activities based on specific change records rather than just relying on timestamps or user IDs. This granular visibility is crucial when you are investigating anomalies, as it provides instant context regarding why a specific administrative action was initiated at a particular time. If an activity occurs without a valid ticket ID, an alert can be triggered in the SIEM or within the CyberArk dashboard to highlight the breach of compliance policy immediately. These configurations play a vital role during audit season, as you can generate comprehensive reports that correlate specific privileged work efforts directly to approved change management tickets. It transforms the act of password management from a technical routine into a transparent business process. See you in the next lecture. Welcome back. Let us discuss how to effectively manage account groups and credential usages within the CyberArk ecosystem. When we talk about managing groups of accounts, we are essentially looking at the requirement to keep credentials synchronized across a collection of endpoints that share the same underlying password. In many enterprise environments, you might encounter a scenario where a single administrative account is replicated across dozens of servers or network devices. Manually updating these passwords individually would be an administrative nightmare and prone to human error, which is why CyberArk provides the functionality to group these accounts. By designating a master account within the vault, the Central Policy Manager, or CPM, can be configured to push password changes to all associated members of that group simultaneously. This ensures that when the CPM triggers a password rotation based on the defined platform policy, every member account is updated in lockstep, effectively eliminating password drift. You should view this as a mechanism to maintain consistency across distributed infrastructure without the overhead of manual updates. Handling usages is a slightly different architectural challenge that arises when a single credential is required by multiple disparate services or automated tasks. Imagine a scenario where a service account is used by 3 different applications to access a database. If you rotate that password, you risk breaking all 3 integrations if they're not updated at the same time. CyberArk handles these usages by allowing you to associate a single managed object in the vault with multiple consumption points, effectively tracking the lifecycle of that credential separately from the services that consume it. This abstraction layer provides a centralized control point, meaning security teams can enforce strict rotation policies while monitoring exactly which services are reliant on that specific set of credentials. When a rotation occurs, the platform logic ensures that the vault updates its internal record, and depending on your configuration, it may trigger notification events or call custom scripts that alert or update the consuming services. This capability is vital for maintaining uptime in complex, multi-service environments where a dependency failure could result in significant operational outages. Synchronization logic becomes particularly sophisticated when we move into clustered environments or load-balanced application server clusters. In these distributed setups, the CPM must possess the intelligence to distinguish between a single logical service and multiple physical server instances that might be hitting the same set of credentials. When a load balancer is in play, there is often a shared configuration that points to a specific account, and the CPM needs to orchestrate the change so that no server is left with an expired password while others are updated. CyberArk platforms manage this through the use of specific platform settings that define how many objects should be updated, the success thresholds required, and the retry logic should a connection fail due to temporary network latency. If the CPM fails to reach one node in a cluster, it must decide whether to stop the process or continue updating the rest, a decision that is governed by the platform's error handling configurations. Understanding this synchronization behavior is essential for ensuring that automated password management does not become a bottleneck or, worse, a source of instability for your production applications. Ultimately, the goal of utilizing account groups and managing usages is to translate the complexity of enterprise credential lifecycles into a streamlined and predictable process. You are moving away from treating every account as an island and instead moving toward a model where credentials are treated as logical assets tied to service health. This requires a strong understanding of how the CPM interacts with targets, specifically regarding how it verifies account availability before attempting a rotation. If you misconfigure these grouping or usage relationships, you might cause a cascade of authentication failures that ripple across your environment, making it nearly impossible to pinpoint which specific service initiated the rejection. Take the time to map your dependencies correctly, ensuring that your automated rotation policies do not conflict with the connection patterns of your production servers. By treating your credential architecture with the same rigor you apply to your network topology, you ensure that security improvements do not come at the cost of operational resilience. See you in the next lecture. Welcome back, everyone. In this lesson, we will focus on the precise configuration of password complexity rules and the mechanics of the CyberArk password generator. When we approach the task of managing privileged credentials, we must acknowledge that a password is only as effective as its inherent entropy and its compatibility with the destination system. Defining complexity requirements is not merely about choosing the longest possible string, but about aligning with the specific constraints of the target OS or application. Within a PAM solution, this requires a methodical approach where we define length, character sets, and forbidden characters at the platform level. If you set a complexity requirement that exceeds what a legacy system like an older mainframe can process, you risk triggering service outages or lockout scenarios. Therefore, the definition of these rules must always be driven by the technical limitations and security policies governing the target resource. By centralizing these settings within the platform policy, CyberArk acts as an enforcement layer that ensures all managed accounts adhere to the required security standard without manual intervention. The CyberArk password generator is a highly flexible engine that performs these enforcement duties during password rotation or manual change operations. You configure this utility within the Platform Management section of the PVWA by navigating to the Password Policy settings. Here, you have the ability to toggle specific character types, such as requiring at least one lowercase letter, one uppercase letter, one digit, and one special character. It is equally important to define which characters are forbidden, specifically those that might cause issues with command line interactions or script execution on your target systems. For instance, while a system might technically accept almost any ASCII character, including a % or an ampersand in a password, can cause scripts to fail or escape improperly during an automated sign-in process. By carefully curated forbidden characters lists, you prevent these downstream operational failures while maintaining the security posture your organization demands. We must consider the nuances of integration when dealing with diverse environments like Active Directory versus Oracle database targets. Active Directory typically handles long, complex passwords quite well, allowing you to maximize length and character variety to combat brute force and dictionary attacks successfully. Conversely, an Oracle database might have specific constraints regarding character set support or maximum length limits depending on the version and the specific driver being utilized. When you configure the password generator, you are effectively creating a contract between the CyberArk Vault and the target system's authentication layer. If the generator creates a password containing a character that the target system's password reconciliation module rejects, the CyberArk CPM will fail to verify the credential successfully. This highlights the importance of testing your platform-level settings against a non-production instance of your target systems before applying them globally to your production environment. Automation of credential management relies entirely on the predictability and adherence of these configured policies. When a CPM policy triggers a rotation, it calls upon the generator, which operates strictly within the boundaries you have provided. If you have defined a policy that mandates a 24-character password with specific symbols, yet that target endpoint only supports 16 characters, the CPM verification will logically fail. This is why you should always map your policy settings to the documentation provided by your infrastructure and application teams. By maintaining this alignment, you reduce the need for manual troubleshooting and ensure that the password rotation lifecycle remains seamless and error-free. The system is designed to provide you with the granular control necessary to balance security requirements with operational stability across the entire enterprise estate. I will see you in the next session. Welcome back. We are now diving into the core of privileged session management, where we focus on the architecture and flow of connections through the PSM. When we discuss the privileged session manager, we are essentially talking about a hardened jump server that acts as a proxy for all privileged sessions. The primary goal here is to isolate the target systems from the end-user workstation, ensuring that no direct connection ever exists between them. From an architectural perspective, the PSM sits between the end user and the target infrastructure, intercepting RDP or SSH traffic. When a user requests a session through the Password Vault web access, the connection is brokered by the Vault and initiated by the PSM server. This process involves the PSM building a secure tunnel, which effectively masks the credentials from the end user. Because the end user never sees the password, we successfully eliminate the risk of credential theft or exposure on the endpoint. This proxy mechanism is the foundation of the CyberArk session management strategy, creating a clean boundary that we can monitor, record, and control with granularity. To facilitate these connections, the architecture relies on two specific functional users residing on the PSM server: PSM Connect and PSMadmin Connect. We often overlook these, but they are critical to the secure operation of the proxy service. The PSM Connect user is the service account that carries out the actual initiation of the session on behalf of the end user. It creates the environment necessary for the redirection of RDP or SSH protocols through the PSM host. On the other hand, the PSM Admin Connect user is primarily utilized for administrative tasks, such as managing the PSM server configuration or performing troubleshooting. Both accounts must be strictly managed within the Vault, and their passwords should be rotated regularly by the central policy manager to ensure they do not become static vulnerabilities. If these accounts are compromised or misconfigured, the entire integrity of your session isolation architecture is at risk, which is why their management is a pillar of secure deployment. Beyond the standard protocols, we often encounter the need to connect to non-standard applications or legacy systems that do not native support RDP or SSH. This is where the universal connector capability becomes essential for a robust PAM implementation. Instead of relying on predefined connection components, a universal connector allows us to wrap an external application launcher to establish the session. It essentially acts as a container for custom scripts or executables that manage the interaction with the target software. By configuring the PSM to identify the specific process and window titles of the destination application, we can automate the login sequence while maintaining the secure proxy layer. This capability effectively extends our reach, ensuring that even the most obscure or proprietary systems can be brought under the umbrella of our session recording and monitoring policies. Managing the PSM server-side prerequisites is a task of continuous hardening and attention to environmental constraints. We have to ensure that the server is physically or logically isolated, with no direct access permitted except from the necessary management segments. The connection flow itself must be supported by a stable and performant network configuration, as the PSM is sensitive to latency and packet loss. We should verify that the required ports for the specific protocols, such as 3389 for RDP or 22 for SSH, are only open to the internal network segments where our target systems reside. Furthermore, the PSM server itself must be treated like a Tier O asset, meaning we restrict administrative access to a very small set of highly trusted personnel and monitor the server for any unauthorized changes to its local policy settings. These prerequisites collectively reinforce the defense-in-depth philosophy, ensuring the proxy serves its purpose without becoming an additional point of weakness. See you in our next discussion. Welcome back. In this lecture, we look into the mechanics of connection components and how they govern the specific protocols utilized by the Privileged Session Manager. To understand the Privileged Session Manager, one must recognize that it acts as a protocol proxy between the end user and the target resource. Connection components such as PSM-RDP, PSM-SSH, and PSM-Web function as the specific drivers that initiate, encapsulate, and facilitate these connections. Each of these components is essentially a configuration object defined within the PVWA that dictates how the PSM server interacts with the target machine. When you initiate a session, the PVWA identifies the platform associated with the account and checks which connection components are mapped to it. This mapping allows an administrator to strictly control whether a user can connect via a graphical interface, a command line, or a browser-based session. It is the architectural glue that ensures that the security requirements defined in the master policy are consistently enforced across all sessions, regardless of the protocol or target technology. Configuring these components requires a solid understanding of the parameter hierarchies defined within the platform settings in the Administration tab. When we associate components with platforms, we are effectively whitelisting the allowed methods of access for that specific set of accounts. If a platform is configured for Windows Server Management, it is typical to see PSM-RDP enabled, but you might also opt to enable PSM-Web if you are facilitating access to cloud-based management consoles. Beyond mere existence, the granular control over these components is where the real maturity of a CyberArk deployment becomes visible. You can modify specific parameters that govern the behavior of the connection, such as the initial window size, the routing of audio, or the presence of the toolbar. By centralizing these settings, you ensure that every administrator connects in a standardized, auditable, and secure manner. One of the most critical aspects of managing the end-user experience involves the redirection settings, which are often sources of both convenience and security risk. Within the connection component parameters, you have the ability to toggle features such as client-side drive mapping, clipboard redirection, and printer redirection for RDP sessions. From a security perspective, allowing clipboard redirection means that a user could potentially copy sensitive data from a remote machine into a local, untrusted document. Conversely, disabling these features might frustrate power users who rely on local print drivers or local file shares to move logs off the target server. You must balance the friction against the risk profile of the target environment. If you are managing PCI DSS compliant systems, it is often considered best practice to disable all unnecessary redirections at the platform level. Creating customized connection experiences serves a dual purpose: simplifying administrative access and enforcing the principle of least privilege. You are not confined to the default stock components provided during the initial installation. By duplicating an existing connection component, you can create a specialized version that enforces specific constraints for a unique user group. For example, you could create a version of PSM SSH that forces a transition through a specific jump server while simultaneously stripping away the ability to use X11 forwarding or agent forwarding. This is achieved by adjusting the underlying parameters of the target settings, which define the command line arguments sent to the PSM executable on the back end. By tailoring these interactions, you ensure that the operational requirements of your IT staff do not bypass the security controls deemed necessary for high-value targets. Ultimately, the goal is to make the connection process as predictable as it is secure. Whether you are tweaking how a web application captures session data or isolating the drives available to an RDP session, your primary tool is the PSM configuration within the platform management interface. Every change you make to a connection component parameter immediately propagates to all accounts assigned to that platform, which makes this a very powerful yet potentially volatile lever. Always test your configuration changes in a pre-production environment to avoid disrupting legitimate administrative workflows. By mastering these components, you elevate yourself from someone who simply installs software to someone who architects secure access paths. This is the foundation upon which secure session monitoring and auditing are built within the CyberArk ecosystem. I will see you in the next lecture. Welcome back. In this session, we will examine the mechanisms behind session recording and the lifecycle of session data within the CyberArk environment. The Privileged Session Manager, or PSM, acts as the primary gateway for privileged access, and its ability to record activity is a cornerstone of audit compliance. When a user establishes a session through the PSM, the component captures not only the visual representation of the session in the form of a video file, but also extensive text-based metadata. This metadata includes keystrokes, window titles, and various system events that provide context to the actions performed by the privileged user. Configurational settings within the PSM's connection components determine the depth and fidelity of this recording, allowing administrators to strike a balance between granular visibility and performance overhead. It is important to remember that these recordings are processed locally on the PSM server before being transmitted to the vault for long-term storage. If the PSM machine runs out of local disk space, the recording process may be interrupted, which highlights the necessity of monitoring the local spooling directories where these files temporarily reside. The transition from the PSM server's local disk to the secure storage of the vault ensures that the evidence is tamper-evident and protected by the same security controls as the account credentials themselves. Once the session recording reaches the vault, the system places it into a specific safe designated for recordings. The life cycle of these recordings within the vault is dictated by the retention policies defined at the safe level. Administrators must carefully configure these retention period settings to comply with organizational data governance requirements while avoiding the exhaustion of the vault's storage capacity. If the retention period is set too long, the storage volume will inevitably grow, potentially impacting the performance of the system or leading to storage capacity alerts that require urgent remediation. Conversely, if the retention period is too short, you risk losing audit trails before they have been reviewed or archived by internal compliance teams. Balancing these settings requires a clear understanding of the regulatory landscape and the frequency at which sessions are generated across your environment. Furthermore, the storage consumption is directly proportional to the resolution, frame rate, and duration of the sessions, making it essential to tune the PSM recording settings according to the actual operational needs rather than relying on default configurations. Effective management of session records also involves monitoring the bandwidth utilized during the upload from the PSM server to the vault. During periods of high activity, the network path between the PSM and the vault can become a bottleneck if the accumulated recording files are not offloaded in a timely and efficient manner. As an administrator, you should verify that the PSM server is correctly configured to manage its local holding folders, ensuring that it cleanly deletes files only after it has received an acknowledgement that they have been safely stored in the vault. If you notice a persistent backlog of files in the PSM recording destination folders, it might indicate network saturation or an issue with the vault's ability to accept incoming data. Monitoring these flows allows for proactive capacity planning and ensures that your audit capability remains robust even during peak operational hours. Consistent oversight of these storage and transfer mechanisms ensures that the PSM fulfills its purpose as a reliable, secure audit tool that satisfies even the most rigorous security audits. I will see you in our next exploration of the architecture. Welcome back. In this lesson, we are going to explore the mechanics of session auditing through keystroke logging and metadata capture within the Privileged Session Manager. When we secure privileged access, the primary objective is visibility. We achieve this through the Privileged Session Manager, which acts as a proxy between the user and the target resource. To enable detailed keystroke logging for SSH sessions, we must configure the platform settings within the Password Vault web access. This involves navigating to the specific platform associated with the target account and ensuring that the recording property is enabled. By default, the recording settings allow for text-based logging of the command stream that passes through the PSM proxy. For Windows sessions based on RDP, the behavior is slightly different because RDP is a graphical protocol rather than a shell-based one. In this scenario, keystroke logging functions by capturing the input events sent to the remote desktop interface. It is essential to understand that this configuration is platform-dependent and requires active policy enforcement at the account level. When these policies are activated, the PSM records every character typed by the privileged user during the established session. This data is then stored alongside the video recording, providing a text-searchable audit trail for auditors and forensic investigators. Beyond simple keystrokes, the PSM provides the capability to capture window titles for Windows sessions. This is a critical feature because it provides context to the administrative actions being performed on the remote server. When an administrator switches between applications or opens system configuration panels on a target Windows machine, the title of the active window is reported to the Vault. We enable this by configuring the PSM parameters for the specific Windows platform. This metadata is not just a passive log. It is actively indexed by the Vault to allow for more granular session auditing. Imagine an auditor needs to verify if a user stayed within the scope of a maintenance task. By reviewing the timeline of captured window titles, the security team can correlate session activity with specific administrative consoles or tools. This granularity shifts the burden of proof from mere video playback, which is time-consuming, to metadata analysis. It effectively creates a structured event log out of an unstructured graphical session, making the audit process significantly more manageable for complex deployments. Once sessions have been recorded and the logs have been processed, the PSM Monitoring tab serves as our primary interface for review. This dashboard acts as a query engine for the recorded session data within the PVWA. When you navigate to this section, you are presented with a list of historical sessions that you can filter based on various criteria. For audit and forensics, searching for specific commands executed during an SSH session is a standard operational procedure. If you are investigating an incident, you can search for specific strings, such as commands involving user creation or service restarts, within the keystroke logs. The search functionality retrieves the exact timestamp when a command was typed, allowing the administrator to jump directly to that point in the session recording. This linkage between the text-based command stream and the visual evidence is what provides a comprehensive view of privileged activity. Maintaining the integrity of these recordings is paramount, so ensure that the Vault policies for retention and compression are correctly applied. By mastering the PSM monitoring interface, you enable your organization to demonstrate compliance readiness at any time. See you in the next lecture. Welcome back to our exploration of the Privileged Session Manager. In this session, we will focus specifically on the real-time operational capabilities regarding active session management and incident mitigation. When we deploy the Privileged Session Manager, we are essentially placing a high-assurance gateway between our privileged users and the target systems they need to manage. While recording sessions provides a valuable audit trail for post-incident investigation, real-time visibility is what fundamentally shifts our posture from reactive to proactive. Within the Password Vault web access interface, authorized users with the appropriate permissions can view a list of all currently active sessions that are being proxied through the PSM. This visibility is not merely a passive status report, but a functional control point where an administrator can hover over a live session to initiate a connection. By selecting to watch a session, you are initiating a parallel observer stream that allows you to see exactly what the privileged user sees in their active window. This capability is essential because it removes the opacity of the connection, ensuring that administrative actions remain transparent and accountable while they are being performed on sensitive infrastructure. The decision to watch a session is a matter of administrative policy that should be clearly defined against your organization's risk appetite. You might choose to monitor certain high-risk administrative tasks, such as database schema changes or domain controller modifications, as a matter of standard operating procedure. When you are watching a session, the PSM ensures that the observer experience mirrors the end-user experience, providing a synchronized view of activity. From a technical perspective, this functionality relies on the established connection between the PVWA, the PSM server, and the target machine, which is why network connectivity and performance are critical. If the observer experiences significant lag in the display, it can hinder the ability to detect malicious keystrokes or unauthorized command execution effectively. Therefore, ensure that your monitoring infrastructure is sized correctly to handle the additional overhead of concurrent observation streams without impacting the primary session performance of the user. Beyond mere observation, the most decisive capability you have at your disposal is the ability to terminate an active session if you detect suspicious or unauthorized behavior. If an auditor or a security administrator identifies activity that violates compliance rules or poses an immediate threat to the environment, they can intervene directly from the PVWA monitoring interface. When you trigger a session termination, the PSM forcibly severs the connection between the user's client workstation and the target system. This action is instantaneous, preventing the execution of further commands or the exfiltration of sensitive data that might follow an initial suspicious entry. It is important to realize that this is a blunt instrument that stops the current session entirely, so it must be used with the understanding that it will interrupt the user's workflow abruptly. Your organization should have a clear policy governing when this kill switch is appropriate to avoid operational disruption caused by accidental or premature termination of legitimate administrative tasks. Implementing these controls effectively requires careful attention to the permissions assigned to the accounts that perform the monitoring. Not every user who has access to the vault needs the capability to terminate sessions. This privilege should be restricted to a small, trusted group of security auditors or privileged account administrators. You must configure the relevant safe and platform settings to ensure that the monitoring users have the necessary view and manage permissions on the sessions they are expected to oversee. If a user tries to intervene but lacks the administrative rights, the system will block the action, rendering them unable to prevent a security breach in progress. Regularly reviewing these access rights is a core component of maintaining a secure PAM environment, as it ensures that your oversight capabilities are distributed along the lines of least privilege. Always document the rationale for your monitoring coverage to ensure that your security practices are defensible during internal and external audits. See you in the next lecture. Welcome back. Today we examine the technical nuances of the Privileged Session Manager for SSH, commonly known as PSM for SSH, or PSMP. The Privileged Session Manager for SSH acts as a transparent proxy between your native SSH client and the target Unix or Linux systems. Unlike the standard PSM, which requires a browser-based interface, the PSM for SSH lets administrators use their preferred terminal emulator, such as PuTTY, iTerm2, or native OpenSSH. By routing connections through this proxy, CyberArk ensures that all privileged activity remains under the watchful eye of the vault. The connection flow essentially involves the user authenticating to the PSMP, which then retrieves credentials from the vault to authenticate against the target server in the background. This design maintains the user's workflow while enforcing security policies that would otherwise be difficult to implement in a decentralized environment. It is an elegant solution for infrastructure teams who prefer the command line interface over graphical alternatives. Configuring these proxy connections requires an understanding of the specific syntax required to bridge the identity of the end user with the target account credentials. Users typically connect using a string formatted as target username at target address at proxy address, which informs the PSMP how to handle the request. Upon reaching the proxy, the system verifies the user session against the vault's defined access policies and permissions. If the request is valid, the PSMP initiates the session, potentially utilizing either password-based or key-based authentication. Key-based authentication is generally preferred in automated or hardened environments because it minimizes the risk of credential leakage during the interactive phase. Selecting the appropriate authentication method requires aligning your security posture with the technical constraints of your target guest operating systems and their configuration. One of the most powerful features available once a connection is established is the granular control over executed commands. Through the platform settings, you can define command blacklists to prevent restricted actions or whitelists to ensure only authorized operations occur on target machines. When a user enters a command, the PSMP inspects the input string against these lists before passing it to the target system. If a match is found on a blacklist, the proxy can reject the command, provide a notification to the user, or terminate the session entirely. This capability is critical for auditing and risk mitigation, especially when dealing with high-value infrastructure or sensitive databases. It provides an essential layer of preventative security that traditional SSH implementations simply do not offer. Integration with native SSH clients requires careful configuration to ensure the authenticity of the proxy is verified, preventing potential man-in-the-middle issues. When users connect with applications like PuTTY, they must trust the SSH host key of the PSMP server itself. In a production environment, you would typically manage these signatures through centralized SSH config files or common trust stores. The PSMP also supports integration with various authentication plugins to ensure that the user identity presented to the proxy is verified correctly against existing directory services. By centralizing this access, you essentially eliminate the need to distribute persistent credentials to end-user workstations. The target Unix systems see the connection coming from the PSMP, effectively masking the true source of the request from the viewpoint of the target node. I will see you in the next lesson. Welcome back. In this lesson, we will focus on the health monitoring of the Privileged Session Manager and the architecture required for high availability. Monitoring the health of your Privileged Session Manager, or PSM, is a critical operation because it sits directly in the path of your most sensitive privileged sessions. You effectively have two primary ways to monitor these services, starting with the internal mechanism of the PSM Health Check page. By default, you can navigate to the health check URL hosted on the PSM server itself, which provides a simple response confirming whether the service is operational. However, in a production-grade environment, relying solely on a single instance is not enough. You must ensure that the core services, such as the CyberArk Privileged Session Manager service and the Remote Desktop Gateway service, are running without interruption. If these services hit a ceiling, often caused by exhausted resources or hung processes, your users will immediately lose the ability to initiate sessions. Monitoring these processes through external tools and alerting on status changes ensures you can respond before a complete system outage occurs. To scale effectively and avoid single points of failure, we deploy PSM in a farm configuration behind a load balancer. When you group multiple PSM servers into a single farm, the goal is to distribute connection requests across the available pool of servers. This allows you to handle increased concurrent workload while providing redundancy if one machine requires maintenance or suffers a hardware failure. The load balancer acts as the front door for your incoming traffic, receiving connection requests from the private ARC usage or the PVWA. It evaluates the health of the individual PSM nodes and forwards the request only to those it deems healthy and ready to accept traffic. If an individual PSM node stops responding, the load balancer identifies the failure during its routine health checks and marks the node as unavailable. This prevents the system from routing users to a dead server, thereby protecting the user experience. The concept of session stickiness, or persistence, is perhaps the most critical configuration detail when implementing a load balancer for PSM. Unlike standard web traffic where you can switch servers between requests without the user noticing, PSM sessions are long-lived, stateful connections. If the load balancer is set to round-robin without persistence, a request might be routed to one PSM server, but the subsequent connection handshake might fail because it is routed to another server that lacks the context of that specific connection. You must configure your load balancer to use source IP affinity or session-based persistence to ensure that once a connection is initiated with a specific PSM node, subsequent packets for that session return to the same physical node. F5, Big IP, and similar enterprise load balancers support persistence profiles specifically designed to maintain this relationship for the duration of the RDP or SSH stream. Failure to configure this correctly typically leads to intermittent session drops that appear randomly to the end user. Troubleshooting PSM connectivity often involves dissecting the interaction between the client, the load balancer, and the target machine. One common area of failure involves certificate mismatches, where the load balancer offloads SSL, but the target server or the PSM itself expects a specific chain of trust. When a user reports a session error, the first step is always checking the PSM logs located on the server, as they often contain specific error codes regarding handshake failures or authentication denials. You must verify that the load balancer certificate and the PSM internal certificates are aligned, particularly in environments using custom PKI hierarchies. If the connection fails before the session is even established, the issue is frequently a service interruption on the PSM server, a locked account, or a misconfigured connection component. Always keep in mind that the PSM needs to authenticate against the vault to initiate these sessions, so if your vault connectivity is degraded, your PSM health status will inevitably reflect that as well. By systematically evaluating the service status from both the local server perspective and the load balancer perspective, you minimize the black box nature of session management. A robust environment thrives on clear health reporting and strict adherence to persistence requirements, ensuring that when an administrator clicks Connect, the session is established predictably and securely. We have covered the essentials of keeping that connection path healthy and reliable. I will see you in our next session. Hello, and welcome back to the course. In this segment, we will explore the Secure Connect feature, a mechanism designed to facilitate privileged access to target systems that have not yet undergone the formal onboarding process within the CyberArk Vault. This capability is explicitly intended to serve ad hoc access requirements where the immediate administrative burden of fully managing a credential must be bypassed temporarily. By leveraging the Privileged Session Manager, or PSM, users can initiate a connection to a target server simply by specifying the address and authentication details at the point of request. This workflow represents a departure from the traditional model, where an account must first reside in a safe and have its password managed by the central policy manager. From an architectural standpoint, the PSM acts as a transparent proxy, effectively extending the reach of our privileged access infrastructure to those edge cases, or emergency scenarios, where traditional onboarding is either not feasible or not yet completed. When we talk about configuring Secure Connect, we are primarily dealing with the settings within the Privileged Session Manager environment and the specific platform configurations that permit such ephemeral connections. It is important to realize that enabling this feature creates an entry point that operates outside the standard lifecycle of an onboarding rule. You must explicitly configure the PSM to accept these ad hoc requests, typically through settings in the PVWA that define which users are authorized to initiate non-onboarded sessions. The security administrator must remain hyper-aware of the fact that this is not a substitute for proper account management. Instead, it is a functional bridge, and the permissions required for a user to perform an ad hoc connection must be audited as rigorously as any other administrative privilege, if not more so, because the target system is not under the immediate automated control of the CPM. There are significant security implications when your organization decides to permit connections to assets that are not yet onboarded. The primary risk is that the target system lacks the visibility and automated credential rotation that typically constitutes the value proposition of a PAM solution. When a user connects to a system via Secure Connect, the password for that account is not stored, verified, or rotated by CyberArk, meaning the session relies entirely on the security posture of the target system itself. Furthermore, while the PSM is capable of recording these sessions and capturing keystroke logs, the audit trail is necessarily different from an onboarded account. You can expect to see the session activity logs within the vault, but you will lack the metadata linking that session to a specific managed object in a safe. This gap can complicate reporting if you are relying on standard compliance audits that expect every session to correlate with a registered account entry. Managing the permissions for this feature requires a meticulous approach to delegating access rights. Users who are granted the ability to use Secure Connect are effectively given a license to bypass the vaulting workflow, which is why this privilege should be restricted to specific user groups or identity sets that have a demonstrated operational mandate for such access. You must verify that the PVWA and PSM components are hardened to prevent unauthorized access to the connection portal itself. It is also beneficial to implement a strict monitoring policy specifically for these ad hoc sessions, ensuring that they are flagged in your security information and event management system with a higher severity level. If a user connects to a target that is eventually onboarded, you must ensure that there is a clear transition path to prevent duplicate session handling or confusion in your audit logs. Use this feature as an exception to your standard operating procedures, not as a shortcut, because the ephemeral nature of these connections creates blind spots that your existing reporting tools might not automatically address without additional custom configuration. See you in the next lecture. Welcome to our final module, where we bring everything together to ensure you are fully prepared for the PAM-DEF examination. In this session, we will consolidate the core concepts of CyberArk administration into a cohesive framework. To master the exam, you need to understand the analytical power provided by the CyberArk reporting infrastructure. Compliance reports are essential for demonstrating that your organization adheres to security standards by providing historical data on password changes and vault access. Activity reports provide a granular view into the day-to-day operations, tracking which users performed, which actions, and when those actions took place. Entitlement reports serve a different purpose entirely, focusing on the current state of vault permissions and identifying potential overprivileged users within your safes. You should think of these reports not just as administrative tasks, but as the proof layer of your entire identity security architecture. When you are sitting for the exam, remember that knowing the distinction between a report that validates a process and a report that validates access levels is a common point of confusion. Effective use of these reports is the primary way you will prove to auditors that your privileged access management implementation is working as intended. Troubleshooting is an inevitability in the life of a PAM administrator, and the exam expects you to be fluent in the language of logs. The italog.log file is the central nervous system of the vault, recording every core transaction and security event that passes through the vault server itself. When you encounter a failure in password rotation, your first destination must be the PM log, which details the specific interactions between the central password manager and the target system. Similarly, the PSM.log is your primary tool for diagnosing issues during active sessions, such as dropped connections or failed recording uploads. You should familiarize yourself with the common error codes, as the exam often presents scenarios where you must map a specific numerical error to a logical root cause. For instance, knowing how to interpret a connectivity error versus an authentication failure in the log files can save you significant time. Do not just memorize the error numbers, but learn to recognize the underlying pattern of communication between the components that usually precedes a failure. Successfully navigating the exam requires a structured approach to managing your time and your knowledge base. When you encounter a complex question, prioritize identifying the core domain being tested, whether it is session management, onboarding methodology, or policy enforcement. If you feel stuck on a scenario-based question, move forward and return to it later to ensure you do not exhaust your time on a single difficult item. Remember that your administrative lifecycle begins with a robust architecture and carries through to the continuous enforcement of the master policy. Your understanding of account onboarding should be holistic, covering everything from manual input to automated discovery and REST API-driven workflows. When you think about session monitoring, visualize the entire chain from the PSM connection component to the final recorded metadata. By anchoring your thoughts to this lifecycle, you create a mental map that helps you answer questions even when the phrasing is complex or unexpected. Attaining the Defender certification is a significant milestone in your career, but it is only the beginning of your professional journey with CyberArk. Once you have solidified these foundational skills, you may want to look toward the Sentry level to deepen your technical expertise in implementation and architecture. The Guardian track follows, which provides the strategic vision necessary to lead large-scale privileged access management initiatives within an enterprise. Each of these certifications builds upon the concepts we have practiced here, reinforcing the importance of secure, scalable, and audit-ready infrastructure. Continue to rely on the official documentation provided by CyberArk, as it remains the authoritative source for every product version update and architectural best practice. You have now established a solid command of the PAM-DEF objectives, and your ability to diagnose and manage the vault is a valuable skill in the cybersecurity domain. I wish you the best of luck on your upcoming examination. See you soon.